Good day. I am Angelica Lazaro, and together with Lawrence Igmen and Francis Omana, we will be discussing our thesis topic entitled Comparative Analysis of Prefabricated and Cast in Place Tunnel Walls in the Metro Manila Subway Using Life Cycle Assessments and BIM Design. For this proposal, an introduction, along with objectives, scopes, limitations, and delimitations, RRL, framework, and methodology will be discussed. To begin with, the Build or BBB program aims to boost the Philippines economy by creating about 1.1 million jobs annually through public infrastructure investment. It has already reduced the unemployment rate, though joblessness persists in areas like the National Capital Region and Calabarzon. With 8.9 trillion pesos allocated, BBB focuses on improving public transport and accessibility, especially in remote areas, helping to balance urban and rural development and enhance the quality of life. Building information modeling or BIM is a key in promoting job productivity and cost reduction. However, there are certain problems that are encountered with the adoption of such, which are high costs and the lack of skill. There are benefits in using this in the construction industry, particularly as it improves sustainability, cost estimation, and scheduling. Currently, the Philippine construction industry still relies on traditional methods like CAD, which hinders its full adoption. The objectives of this thesis are the following. Number one is to investigate the life cycle environmental impacts of prefabricated and cast in place subway construction using BIM to model and quantify the environmental footprint at each stage, from material production to operation and maintenance. Second is to formulate a method targeted in addressing interoperability and data transfer from BIM LCA software for minimizing inaccuracies in sustainability assessments. Lastly, is to develop a framework for subway station and tunnel construction following cost and time efficiencies through the use of BIM considering long-term economic and environmental benefits through MIVES and parametric analysis based on comparative analysis of two lines.
For the scope and limitations, this project conducts a cradle to grave life cycle analysis of emissions for two subway stations, from East Valenzuela Station to Quirino Highway Station and Tandang Sora Station to North Avenue Station, using data from contractors, evaluating software interoperability between AutoRevit and SimaPro to streamline emission analysis throughout the construction life cycle. The study aims to assess sustainability and environmental impact, identifying areas where carbon emissions can be estimated and improved in subway construction.
For the first section of the literature review, which is BIM integration challenges and benefits in the construction industry, it was mentioned by Olan Rawaju et al. 2022 that developing countries such as Nigeria face problems such as software compatibility, lack of standards, and limited user experience, which hinder the full adoption of BIM technology. Therefore, awareness and usage of BIM may resolve these issues. Meanwhile, in a study by Ong Peng 2018, traditional and steel deck formwork methods were compared, and it was found that steel deck method is more costly, however, it offers a more time efficient approach. This study also showed that BIM is effective in project management and that it promotes sustainability and optimization for material and energy use. Lastly, in a study by Santos et al. 2020, they stressed on standardized data structures, object libraries, and simplified data for enhancing the interoperability of BIM software.
Moving on to the next section of our literature review, which is BIM assessment methodologies for time, cost, and sustainability. In the literature by Lozano et al. 2023, the study focused on using an analysis method named Integrated Value Model for Sustainability Assessment, or MIVES. This method incorporates a series of steps of calculations and selects optimal alternatives of the developed model using this decision-making tree approach. However, the research lacked real-time collection data for cost and time variables and mainly relied on theoretical values and assumptions. In this case, the method of analysis may need some evaluation of its accuracy and applicability of results. Nevertheless, this analysis of method can contribute in developing an adaptable framework for quantifying implications of changes made throughout the construction of the Metro Manila subway in terms of sustainability. On the other hand, Hidayat-Zadeh et al. 2024 asserted that there is a need to account for geohazard information when analyzing tunnel constructions, since this may affect the accuracy of the developed BIM model. In order to consider varying geotechnical data at the site, they proposed the following framework, wherein it used geographic information system, tools such as Rhino plus Grasshopper and Flap 3D. These softwares are integrated into BIM softwares such as AutoRevit to improve model data. The study did show the accuracy and effectiveness of the model design did improve. The next set of literature will be discussing ISO frameworks and lifecycle assessments. On another narrative, Tam et al. 2020 laid out a comprehensive framework for standardizing integration of BIM and LCA, which is an essential process of this study. These guidelines are under the ISO 14040 framework. It includes three phases. The first one is lifecycle inventory analysis, collection of data, lifecycle impact assessment, which is assessing the additional information from BIM, and lifecycle interpretation, which is compilation and assessment of results. Zhao and his fellow researchers, meanwhile, used the following equations in determining total emissions, specifically for prefabricated material construction of tunnel arcs. The formulas aided them in finding out that incorporating prefabricated materials in the construction are much more efficient and reduce significant amount of material usage.
For BIM-LCA integration for emission quantification and interpretation, building information modeling has a wide range of applications that are crucial for evaluating material specifications and assessing the environmental impact of buildings, particularly within the framework of life cycle inventory. In a research conducted by Vadati Kaki et al., three implementation methods were proposed for optimizing BIM-LCA integration across different design stages, which are early design, detailed design, and construction design. A study conducted by Hussein et al. Has streamlined the application of building information modeling in assessing the sustainability dimensions of construction projects. This research may serve as a primary reference for developing a framework aimed at conducting life cycle assessments for subway systems. However, despite its notable findings in the field, this study was not able to fully automate the process of the model, which can make it susceptible to human errors. For the energy emissions reduction, Gao et al. Stated that a building's life cycle can be put into five stages, namely the material production, transportation stage, on site construction stage, operation and maintenance stage, and demolition and recycling stage, as seen on the figure on the left. In the analysis of a life cycle of a building, environmental product declarations or EPDs are inputted to enable real time data analysis in softwares such as SimaPro. It was also found that inaccuracies are inevitable due to databases which lack precision on data on carbon emission values. Besides this, a downside to BIM LCA is that it can yield higher building design costs, which can affect the efficiency of the construction of the building. A framework for improving software interoperability has been proposed, focusing on integrating BIM into lifecycle analysis to evaluate infrastructure sustainability. The process begins with BIM using inputs based on ISO 14041, such as the bill of quantities, material geometry, and power demand data for the entire lifecycle of a building. Next, lifecycle assessment is conducted with CIMA-PRO, which evaluates environmental impacts from material manufacturing to the end of life stage. Outputs based on ISO 14043 include metrics like waste emissions, sustainability index, emission factors, and time and cost. Then, the analysis of alternatives are done using parametric life cycle carbon assessment and the prioritization or the assessment of the different environmental impacts of the building by identifying critical areas where action is needed for the efficiency of the project. Time and cost will then be assessed by the use of cubic cost as a cost estimation tool. This step ensures that the environmental considerations align with financial efficiency and if the project would be economically feasible.
Now moving on to our research methodology. For our research design, the study would both be qualitative and quantitative throughout the data gathering and processing. Such all data will be inputted or results of BIM software and its plugins and other analysis softwares that will be used. The subway model that will be used will be embedded with necessary data, such as its specifications. The other analysis software would yield the sustainability indices and emission factors. Data collection would be derived from the ISO 14040 for lifecycle inventory, wherein bill of quantities, material geometry, and power demand are primary inputs. Non-disclosure agreement would have to be arranged in order to secure confidentiality terms between the involved companies and the study itself. Then, data analysis would first make use of the analytical hierarchy process derived from the MIMES method. Tally plugin from Revit would be introduced. For lifecycle assessment analysis, SimaBro would be utilized. Cubicos for cost efficiencies, and an uncertainty analysis for data validation.
Thank you for listening, and if you have any questions, feel free to ask.